he got his PhD in 2005 from Penn State. After that, he's been traveling around, first as postdoc fellows at Carnegie, and then he moved on to the NASA postdoc at Goddard. And then I think since 2011, you joined the Space Telescope, and basically he's been there since then.
Yes.
Yeah.
So traveling around means staying within the mid-Atlantic region for the past 15 years or so. But yes, thank you very much, C.
And I guess another fun part is officially you also work for Aura, right? And I guess so
Yes.
we're under the same system.
Yes,
yeah.
that's right. We all have
Okay.
the same parent company, right? So,
Exactly.
yeah, I'm currently the STIS team lead at the Institute. So I take care of the scientific operations for the STIS instrument on Hubble. So that's the 50% of my functional time, as we call it here. And yeah, I rolled the dice and I got planet formation. So that's what we're talking about today. But if you have any questions about white dwarfs or dusty white dwarfs, feel free to stop by. I'm here until Friday at least. And so I'm more than happy to entertain a chat or two or whatever. So yeah.
Are you doing an observing run?
I am observing at Keck, yes. Sunday night? I better get the night.
Monday night.
Monday night,
Yeah.
yeah, okay. I gotta get that right. It would be bad if I show up too late for that. But yeah, and that's on a white dwarf, so. And that's in collaboration with C. So anyway, I'm gonna talk about circumstellar disks in the time domain, and yeah, I'm putting a plug for Amy Steele, who's in the back corner and looking embarrassed now, which was my goal. So Amy is a grad student at the University of Maryland. She's helping me on the observing run and also collaborating with C. So she's going to, so feel free to talk to her as well, because she has her own scientific interests. And she's going to be doing an informal chat on Friday. So be sure to show up for that. And the only point to this slide is just to remind everyone, planet formation seems really robust in this galaxy, or probably in any galaxy. We see evidence of planetary systems around all different types of stars, all different sort of stages of stellar evolution even. And so I have a few pictures that sort of point that out. You know, this is just sort of a press release image, I think, of the TRAPPIST system. So right, this is a very low mass star, barely an M dwarf, and it has 7 planets. We've got Kappa Corona Borealis, which is a first descent subgiant star, so it has left the main sequence and is becoming a red giant. We have, this is another press releasey image of the transiting debris around WD 1145 plus 017. So up to maybe as many as 50% of white dwarfs show some evidence of having planetary systems, or at least having dust and minor bodies. And then what sort of officially kicked off exoplanet, at least in my mind, and that's because I come from Penn State. So Alexander Wolshin and his co-author Frail found evidence for planetary systems around a pulsar. So if you can find planets around a pulsar, I kind of feel like planet formation is a really robust process in the Milky Way. And so one of the things that I'm really interested in is just trying to understand how and when you find evidence for planetary systems at different stages of stellar evolution. And Amy is working on the giant stars and the white dwarfs as well. So be sure to talk to her about that. And one of the things, right, is we sort of want to understand, you know, what are the initial conditions of planet formation? Where do planets form? When do they form? With what chemistry do they form? What interaction they have on star formation and the disk that you have, the protoplanetary disk that you have, sort of at the later stages of star formation. And so, you know, sort of going from protoplanetary to debris disks, we're now in the phase where we have enough quality of data and enough epochs of data that we can start taking observations of these systems, these circumstellar systems, sort of into the time domain. We can look at more than one image of these systems over time and see if they're changing on human timescales. And as part of this study, you know, we can't really take direct images of sort of the regions of planet formation that we're most interested in. So looking in the time domain sort of helps you with this, and I'll get back to that later. But if you just take our own sort of simple picture of part of the solar system and you put it at 100 parsecs, the angular scales are pretty challenging, even with the amazing instrumentation and observational capabilities that we have. And so I have circles that are roughly representative of the spatial resolution of some various observatories or instrumentations. So some of the more extended configurations of ALMA get you too close to 1 AU spatial resolution, or so that's sort of the smallest scales you can really, physical scales you can resolve. And then it actually gets worse for direct imaging, right, where we don't have interferometry. And so for James Webb, SPHERE, or GPI, these are our sort of best chances of looking at protoplanetary disks in kind of a direct optical or infrared imaging. And the size scales there are just at the limit of sort of understanding what's going on at sort of giant planet forming regions. So we're not going to do it by just taking pictures. We're going to have use other means. And so primarily people have used things like spectral energy distributions of disks to understand sort of what's going on at the inner edges of disks. And there are other also interferometry options in the near infrared and mid infrared that can get you sort of on the scales that you're looking at. But this is a challenge for trying to understand what's going on as planets are forming. But we are in a really exciting time where the images of our disks and the spatial resolution we do have is at a level where our figures for disks are getting increasingly complicated. As you can see by all the annotations on this particular image, you have, this is sort of a nearly face-on Herbig AEBE protoplanetary disk. So this is a disk that's rich in gas and dust. And it shows these beautiful grand design sort of spiral arms, right? And then there's a lot of other features that you can sort of label, but you can notice that the surface brightness of the arms is not constant with azimuthal or position angle. You can maybe see weird fuzzy things going on here, which probably is instrumental, but it's pretty complex, and trying to understand everything that's going on can be quite a challenge. But some of these structures may also be indicative of shadowing that's going on in this outer disk. I'll talk more about that later. That's in the mix here, along with sort of the physical structure of things. We also see, I was just sort of thinking about this, primarily for the more massive stars, we see a lot of these more complex spirals and stuff like that. But for the lower mass stars, we tend to see more like just concentric rings. And that's not, so we're starting to see some patterns in terms of different stellar types maybe having different overall structures. But this is TW Hya. This is from a press release that I was involved in a few years ago, where we had made the claim that there's a gap in this face-on disk. So you have the disk, since these are chronographic observations, the innermost regions of the disk are just not available to you, so they're sort of masked out. And because of the surface brightness, radial surface brightness distribution, you can see that there's sort of like a decrement in flux. And a lot of times when you're looking at scattered light images of disks, this is what this is in the near infrared, oftentimes people scale the surface brightness of each pixel in an image by the radius from the star squared, because that sort of pulls out sort of the more subtle features in the disks. In this case, you sort of see this gap-like feature. And a real question is, why do these spiral arms form? Why do you see gaps in disks? People like to say that this is due to planets, but that may not be the only explanation for why we see these things. For example, this is a series of plots by Dong et al. 2015. So a little complex, but what you really just need to see is, right, so the structure of the disk can actually have an impact on the surface brightness distribution you observe. So, if you have sort of a self-shadowing situation, you can actually get a faux gap in your disk just from the self-shadowing. And Dong had done many different radiative transfer models of different types of disks to sort of demonstrate that you could perhaps reproduce gaps this way. Other people have noticed, even in the submillimeter images of some stars, that there are these multiple gaps. And they have attributed this to perhaps complex planetary architectures. Maybe there is a bunch of protoplanets living in these gaps and creating the gaps, or it could be something more chemically related, right? Because you can get these gaps and rings from pressure maxima or minima in the disk. And that can be caused by concentric rings of snow lines of various materials. So like maybe a CO snow line, just like we have a water snow line that we talk about often in protoplanetary disks. There are many other sort of solid state things that condense out of the gas, and at each point you expect a jump in the surface density of solids at each one of those positions. So perhaps these rings coincide with just changes in chemistry. It's still a little bit up in the air what's going on. But in principle, you could look at a combination of millimeter observations, submillimeter observations like with ALMA, and scattered light observations, and use the two to sort of get at a multi-wavelength picture as to what's going on. None of that necessarily requires you to look at these at multiple epochs to learn things, but this is part of trying to understand the origin of these structures.
Are you saying that the snow line, various snow lines correspond to changes in the scattering probability?
Well,
or
so
what? Is that why?
the important thing to remember, so in the two types of disks, when you're looking at scattered light imaging, for debris disks, when you're in an optically thin situation, what you see essentially is what you get. You see every dust grain that's participating. When you're talking about a protoplanetary disk, when you have optically thick situation, you're much more sensitive to things like self-shadowing, to surface features on the disk, right? Because you're not probing all the way to the disk midplane. There's a lot more to take into account. And then if you add on top of it that a lot of the images that you're now seeing, especially from the ground, these are polarized intensity observations. So you're only looking at the polarized component of the scattered light. And that is modified by geometrical effects. You know, the surface brightness distribution as a function of position angle for a protoplanetary disk in polarized intensity can look quite different than a total intensity image, simply just by the geometry or flaring of the disk.
But how does the snow line have to do with that?
Well, the snow line, if you have a sudden pressure maximum or minimum, you're basically changing the scale height of the disk as well. And so while you're not probing the midplane, you can still infer about things going on in the midplane by how puffy or compact the disk is at any given radius. And that would show up as a change in surface brightness.
It's related to various snow lines for CO and water ice or whatever.
Yeah, I mean, that's a potential idea. Whether that works in practice, I think, is still an open question. I mean, you need sort of many lines of evidence to really tell you what might be going on. And I want to leave you with a sense of uncertainty and dread whenever someone looks at these observations and tries to come up with an explanation, because there are a lot of things that go into this. And if you don't have a good understanding of both how you get a scattered light image and how you get a submillimeter image, you can be led astray just by the pictures that your eyes are looking at. And of course, you can appeal to the fact that there are massive bodies that are forming planets in these systems that are also causing these structures, that you're actually seeing some hint of clearing due to the gravity of a protoplanet. So what I'm showing here is a figure from Valerie Rapson's 2015 paper where they took GPI data of TW Hydra and they compared the data that they got with radiative transfer models where they had embedded a planet in the disk and ran the hydrodynamic simulation and tried to reproduce the images that you see. So these are the real data. These are the models based on the hydrodynamical simulations. And then if you sort of degrade the models to fit the signal to noise of your data, you can see a qualitative, perhaps, agreement. But again, the devil's in the details. Now, in addition to the gaps, we are also starting to see shadow features in these protoplanetary disks as well. So these are a series of images, both from GPI and sphere at various bands, Y, J, and K, and even H. And I'm talking about these features here, right? You're seeing sort of a dip in the surface brightness at very particular position angles. These are sharp, deep dips. They show up at multiple wavelengths, and they show up both in, I think, polarized and total intensity. And so the interpretation is that you're seeing actually sharp features, shadow features from an unseen inner disk. If you get a misaligned disk, you're only seeing the line of nodes of that inner disk shadowing the outer disk. So you get these very nice sharp features. And so I think the relative inclination that they assume for this inner disk is something like 40 or 50 degrees from the outer. So it's quite impressively big in terms of a mismatch. But that, if you think about it, you know, we see for transiting exoplanets, we see this, you know, this relative obliquity of both the planet and the star's rotation axis can be misaligned quite a bit. And generally, we find that through the Roster-McLaughlin effect, I believe. I think I got that right. And in any case, you know, this misalignment of the rotation axes of both the planet and the star tells you something about how misaligned the disk that the planet formed in might be relative to the star, or maybe there was some sort of cataclysmic thing that moved the planet around. But in any case, the fact that we're seeing very misaligned disks, you know, forming planets, that somewhat, you know, ties into these observations that we have of sort of the orbits of planetary systems.
How do you get the shadow features not to be in a 180-degree line with each other?
You get that because the disk itself is flared.
Okay.
And so that offsets the angles a little bit. I believe it's a combination of both inclination and how, you know, what the scale height of the disk is at any given radius.
So why can't you see any sign whatsoever of this invisible disk?
Because it's really tiny. So it's hiding under sort of the mask, the chronographic mask.
Okay.
You know, so in this, right, so in this, we're talking about 30, 40, 50 AU. The disk is probably at 1 to 2 AU. It's like, it's very compact. Here's another example. And we also know that there are disks at these sort of shorter radii, right? Because you have mid-infrared flux at wavelengths that correspond to temperatures at a few AU. So you know there's a disk there. You just can't spatially resolve it. Yeah. This is another example. This is HD 142527. This has an M dwarf companion, sort of somewhere around here, and the M dwarf is basically participated in clearing out this huge gap in the disk. But again, you can see these shadow-like features, and of course, there's an inner compact disk that's misaligned with this outer one. And this is the basic picture, right? You have, I was just saying, you have your line of nodes that creates the shadow, and then you're not shadowing the outer part of the disk in these regions simply because you just are not blocking the starlight. So this is sort of the basic picture of these shadow-like features that people see. Okay, so I'm going to shift to TW Hydra because this is one of the few disks where we've actually taken multiple images of the disk over more than a decade of time, and that's thanks to the Hubble Space Telescope. I'm coming from the Space Telescope Science Institute, so you're not going to be surprised that I'm going to tout Hubble's utility in these kinds of observations. So so Hubble has been, or TW Hydra has been observed with a large fraction of the instruments that have ever been on Hubble. There are WIFPIC 2 observations of Hubble that I don't show, but were taken sort of right after the installation of NICMOS and STIS in the, I guess, servicing mission 2. And then, so NICMOS took some epochs of observation. STIS observed the TW Hydra. NICMOS again, this time with the polarizing filters. And then also in the medium band filters in 2005 with NICMOS. So NICMOS and STIS have taken 5 or 6 images of the disk over the past 15 or so years. And then if you put that all together, you can get sort of a scattered light spectrum of the disk. You can get, you can look for changes in the disk with time. In addition, TW Hydra has been spatially resolved in the submillimeter with ALMA. This is Sean Andrews' very nice paper where they found an interesting gap at 1 AU in the submillimeter, then another, I think, at like 10 or 12 AU, and then 20 AU. I believe those are the different gaps. So this thing is, it's turtles all the way down. There's just gaps everywhere in this disk. So either a lot of different ices are forming, or there's a lot of planets, or who knows what. But it's an interesting system. And since it's one of the closest examples of a protoplanetary disk, and it's nearly just laid out for you practically face on, it's a really great system to study. In fact, if you ever write a paper on TW Hydra, you constantly have to be checking ADS because someone's publishing a paper on it just about every day. In addition, in scattered light with SPHERE, there are multiple gaps as well. There's one at about 80 AU here. This is a 20 AU gap. And then in sort of at 5 to 6 AU, there's a sense of a gap there as well. So the gaps in the middle submillimeter don't quite exactly line up with the gaps that we see in scattered light either, which is somewhat unusual. This is a polarized intensity near infrared image of TW Hydra with SPHERE. At about the same time that everyone was observing it with GPI and SPHERE, I had a program to look at it with the STIS instrument on Hubble. And this is the focal plane of the STIS 50 Perron aperture. So STIS is basically the Swiss Army knife of Hubble. It does a little bit of everything, not so great. And that's evidenced by the coronagraph on board STIS, which is not really a true coronagraph as you might think of it or are familiar with GPI or SPHERE, where you have a very high order adaptive optics system that's feeding into an optimized coronagraph that has a focal plane mask that's probably fairly complex, and you have a LEO stop that undersizes the aperture to basically push down the diffraction pattern of your telescope so that you can look for faint things. In addition, on the high order adaptive optics systems, you actually create a dark hole. You know, GPI is a great example of that, right, over a limited range of angles. With STIS, you basically have these wedges in the focal plane, or these bars, bar 10 and bar 5. So you put your star behind that, and then there's a slightly undersized LEO stop in the pupil plane, which basically doesn't take care of your support mirror structures, so you still get diffraction spikes, but it does tamp down the sort of the wings of the PSF a little bit. So we had literally the least well-designed coronagraph you could possibly imagine, but this was state-of-the-art for space astronomy in 1997, right? That was what you could fly without NASA getting really, cranky at you. But the nice thing is we're in space, so everything's really stable. We don't have the atmosphere to worry about. So you can have your terrible coronagraph, and that's okay because you can do things like observing a reference star along with your target, observing at multiple spacecraft orientations. And if you put that all together, you can actually get results that are still, with your 1997 pretty lousy coronagraph, as good or better than what you can do in the ground. And of course, there are some things that the ground does better, and there are some things that space does better, and I'll talk to you about that. But I had recently participated in commissioning a new aperture location on this little bar 5 aperture. This is called the bent finger, right? It was not designed to look like this. It was just a straight bar, but someone at Ball probably, as they were getting their coffee, kind of slipped a little bit and knocked it, and it got bent. And so it was literally ignored by everyone on the STIS instrument team, instrument development team, on the STIS team at Space Telescope for about 15 or 16 years. They just didn't want to touch it because they didn't know how floppy it might be, whether it was in focus, all these different things, until Andras Gaspar and Glenn Schneider at the University of Arizona came along and said, we should be able to use this. So they had a special calibration program. We call these outsourced calibration programs, where people from outside the institute actually proposed to calibrate new modes in the instrument, and they demonstrated that indeed you can get really good data with this bar 5. And the nice thing about bar 5 is its width is about 300 milliarc seconds on the sky, and so you can get much better inner working angles than any of the other wedge locations on STIS. So if you have anything that you want to do in terms of coronography in space and the visible, in total intensity light, come talk to me and I'll be happy to tell you how to design that program and propose for it. But basically what you can do is you can combine bar 5 observations with one of the other wedge positions to optimize your azimuthal coverage of an object. And so within 1 or 2 visits, and with 1 or 2 changes of the spacecraft orientation, you can get nearly 360-degree coverage and a pretty small inner working angle. So if you can see, right, that your wedge along wedge A is sort of going primarily up and down, and your bar is going left to right. So if you combine the two, you can get a pretty good coverage of whatever you're trying to look at. And that's basically what I did for TW Hydra. I basically said, well, with this new mode on STIS, we can go back to this object that had been observed in 2000 with STIS. You can see that if you take 2 spacecraft orientations, that wedge, those wedges where you don't have any information sort of overlap a little bit. And you get this sort of weird pattern where you're missing parts of the disk. So you can go from this in 2 visits of STIS. And then just for reference, I'm showing the GPI field of view, which you might be interested in. And then in 2015, when we took the observations, we got nearly full coverage down to ½ an arc second, and our best inner working angle was sort of about 0.25 arc seconds, right? And if you compare that to GPI, I think GPI's inner working angle is sort of 0.1 to 0.2 arc seconds. So comparable to GPI's inner working angle, but you also get everything out to 4 or 5 arc seconds in this very large disk. And then just to compare with Sphere, right, because Sphere has Zimpole, which actually goes down into optical wavelengths, 0.6 and 0.8 microns. These are the observations. So the ground definitely wins in terms of spatial resolution, right? Bigger telescopes. But in terms of sensitivity, it's not so great. And also we deal in total intensity light rather than here, these are polarized intensity images. So STIS gets much better sensitivity. So if you have a very faint structure, it's probably preferred. If you want to go to shorter wavelengths, it's possibly preferred as well. But there are definite advantages to one or the other. And so you just have to think carefully about what you might be interested in doing, whether you want STIS or one of the ground-based telescopes. And just to hammer the point of sensitivity, this is roughly the Sphere detection limit for roughly the same total amount of exposure time, give or take. And then this is the surface brightness profile in millijansky's per arc seconds as a function of physical radius, and then you have the radius in arc seconds. Sphere basically detected down to about this level. With deep HST images, you can go down several orders of magnitude to see that the disk extends out to even about 400 AU away from the star, which was bigger than people realized. And we get very repeatable results. The disk surface brightness that we measured in 2000 versus 2015 to 2016 is comparable to within 5 or 10% over 15 years, which is pretty cool. So this sort of says, oh, nothing's really changing, right? You can also take all the images of TW Hydra at the different wavelengths, and you can construct a very coarse scattered light spectrum of the disk at different radii. So that's just what we're showing here. Everything's relative to the visible STIS band, but you can see that broadly speaking, the disk is kind of bluish, which is what you would expect for sort of small dust grains, primarily working in this optically thick disk. And you can compare GPI's polarized intensity radial surface brightness profile, now multiplied by R². This really brings out the sort of gappy nature of the disk in scattered light, and you can compare that to the surface brightness distribution of ALMA. So you have this gap at 1 AU, and then this is the 5 or 6-ish. There's something going on there. There's sort of a kink there. That's 10, 12 AU, 22 AU. So there's a slight match between maybe this gap. And then eventually ALMA loses sensitivity, and we don't know what's going on too much beyond that. But there's a slight match between some of these structures, but not others. And why that is, we don't know yet. Okay, so if we look at just the STIS data, we look at 2000, 2015, and then when my observations were first scheduled, I had a total of 6 orbits on TW Hydra. And because of how I designed the observations, the visits were actually scheduled, one in 2015 and the other in 2016. So scheduling on Hubble is always interesting, right? Because if you have a lot of constraints, it takes a while for your observations to get scheduled. And when I first saw this, I was thinking, oh, this is terrible. It's going to take like 3 years to get a paper out just because I'll be waiting. But it turned out to be lucky, because when I looked at the 2015 and the 2000 data, I was like, if you just sort of go back and forth, you can see that the azimuthal structure in the disk looks slightly different. And then if you look at it in 2016, we can really see that where the disk gets brightest sort of changes with angle. So I noticed this and tried to follow this up. So I went back into the archive and I tried to measure the sort of the position angle of the brightness in the disk, right? So there seems to be a preferred location. And this was known in 2000, like Aki Roberge in 2005 published this really nice paper on the first epoch of STIS data, and noticed that there was an azimuthal asymmetry in the surface brightness profile. And the assumption that this was a geometric effect, that either there was forward scattering dust grains, or maybe there was something in the inner system that was causing this asymmetry. But whatever it was assumed that it would just stay there. And that's not the case. It moves with time. So now if you actually just take position angle and surface brightness as a function of position angle for various radii, if you squint, you can see that the peak is happening at slightly different angles. This is not the best way to show that, but it becomes much more obvious if you go back to the other epochs of data, or if you just fit these sinusoids, right, and you measure the position angle, you can look at just 2015 minus 2016. So in 1 year, the position angle roughly changes by about 15 to 20 degrees per year. It's pretty big. Although it doesn't seem to occur in the inner system for whatever reason. But now if you go back in time and you look at all the different Hubble epochs of data, both in the optical and the near infrared, if you look at one radius, you can see that the position angle changes quite a bit with time. And it seems to be going, it looks like it's oscillating, but that's just an aliasing effect, right? We've made one revolution essentially in this structure. So you can sort of assume that what you're looking at is a rigidly rotating situation with a period of about 16 years. And when you fit all the position angles as a function of radius and take sort of the average position angle and look at this as a function of time, you can fit this with just a constantly rotating feature with a period of about 16 years. So what is this, right? What, if you have something that appears to rotate over a range of radii with a single period, this is not Keplerian rotation. So the assumption is that this is a shadow of some kind in the disk that's rotating with time. And to my knowledge, this is the first time that anyone has had as many epochs to really nail down what the period of this shadowing is doing. A lot of other disks have shown evidence of sort of variable shadowing, but no one has had as many opportunities to really nail down what the sort of typical period is. And at least for this system, it's on the 16-year period. So you can make sort of just a toy model of this and sort of run it through time, right? Just to have a pretty movie. And you'll see that sort of in the late 2020s, we're going to come back around to a part of time where we just don't have much information that we had previously. So if you go back to this one, we've sort of covered this phase of evolution, right? But we don't really know sort of whether we see this going all the way around, right? So you could maybe come up with some sort of weird sinusoidal variation that could explain this, but to the best of our knowledge, it's just going around in a pure circle. Now, we can also look at the azimuthal variation with other observatories, right? So, and at other wavelengths. And so this is, but you have to remember that both sphere and GPI are in polarized intensity, and we don't see nearly the level of variation that we see with STIS. There's, sphere shows some significant bumps and wiggles, but they don't quite match up to what we see at STIS. This is all roughly taken within a few months of each other, these observations. So you can't, claim that things are moving around. So this was a little bit puzzling to me when I published the paper on the shadow with TW Hydra. But Charles Potita at the Institute has just submitted, and hopefully will have accepted soon, this paper looking more in depth at the NICMOS polarized intensity images of this disk. So now we've got Hubble, right, up in space, which hopefully is a little bit more steady. But what you see in the polarized versus unpolarized light, you see that the polarized light doesn't have as large an asymmetry, right, in whatever's going on. And this could be because with this disk, you probably have a lot of multiple scattering going on. And if there is a shadow, then you have maybe less multiple scattering going on within the shadow. And so that could be explaining the slight difference between polarized versus total intensity light, yeah?
So what is causing the shadowing? Is also an inner disk incline?
Yeah, so that's what I'm getting to. But yes, if you sort of take a step back, the assumption here is that we have sort of an inner disk that's misaligned with the outer disk that's causing the shadow.
But what is the radii of the inner disk to cause the shadowing?
Well, that's a good question. I'll get there. But if we assume that this is a shadow, and if we assume that an inner disk is doing it, we can try to make some predictions on where this disk might be. And then just sort of as a side note, back in 2012, Rosenfeld et al. Predicted that there might be a warp in the inner disk at about 5 AU, and they could use that warp based both on submillimeter gas observations and on Aki's data to sort of suggest, well, maybe if there is a warp, you could explain the azimuthal surface brightness variation with this warp. So that's actually pretty promising now, because it's clearly not like forward scattering grains, because this thing is moving. So a warp that's actually precessing or orbiting with a 16-year period seems like a good explanation. And really, warp versus misaligned disk is kind of, they're pretty much the same thing. One, it's just a question of whether there's sort of like a gap between the two, or whether it's just sort of one continuous feature. And then this is a nice paper by Long et al. That just shows what the surface brightness variations actually look like as a function of misalignment angle, right? So as you get to higher and higher misalignment angles, you get these sharper and sharper line of nodes type features. But if you're in the situation where you have a moderate inclination difference, you basically see what you see with TW Hydra, where half the disk is kind of in shadow and the other half is not. So we favor something sort of at the 10-ish degree level. Actually, I want to make sure I'm not running out of time. Is there a clock? Okay. I don't know. 10 more minutes? Does that sound good? Before people get antsy? Great. Okay. So I'll cut to the chase. So if you have a 16-year orbital period, or a 16-year period for this shadow moving around, and you have a situation like this, you could claim that this is due to a perturbing mass, right? That's forcing an inner misaligned disk to move around, right? It's torquing it. So that either means that you're at the actual Keplerian orbital period, and that's 16 years. So if you have a mass of the star and you have a period, you can get at where this object must lie. And of course, you know that from the ALMA data that there are particular locations where there seem to be gaps, right? So the deepest gap actually is at 1 AU. So if we fix that this must be where a perturber must be, then then this becomes a precession timescale. And if there are some papers that allow you to estimate what mass you need to sort of torque an inner disk on some precession timescale. And when you go through that calculation, you can look at the details in my paper, you get sort of about 1 Jupiter mass as your perturber mass. And then if you're actually at 5.6 AU, And if that's sort of where the perturber is driving things, then you're driving things at the orbital timescale, and you need something like 19 Jupiter masses to do it, which is pretty massive and probably not likely. So we favor that there must be sort of a Jupiter mass object at about 1 AU for this, for TW Hydra. And the nice thing is, if you get lucky with, whether, if the planet is more aligned with the inner disk rather than the outer disk, then you actually have a pretty large radial velocity signal to work with. So people like Peter Plavchin, who has a near-infrared radial velocity survey, could look at this star over multiple epochs over a year or two and hopefully see the orbital variation due to radial velocity changes.
I'm sorry, I'm a little puzzled. Those two different radii,
Yeah.
distances would imply quite different orbital periods. So, but
Yes.
you constrained by the rate at which the shadow is progressing, and doesn't it?
Right. So in this case, the planet is massive enough that it's directly coupled to the disk, and you're
Just
moving
pulling it
things
right
on
along.
the orbital timescale.
Okay.
In this case, the object is perturbing and torquing the disk, and so there's a precession to the disk that is some multiple
But not
of
tied to
the
the orbit.
planet's orbital period. Right, and sort of intuitively, right, the less massive thing has to go around many, many times to sort of push that disk around versus a more massive object. And so I'm going to give a shout out to another grad student that I'm working with, who's also sort of leveraging old Hubble data with new data reduction techniques. So this is Ben Wren, he's at the Johns Hopkins University, and he has a nice new way of processing high contrast imaging data to bring out face-on disks better. So if you're familiar with post-processing of high contrast imaging data, typically Loki or CLIP or any of these sort of post-processing methods tend to rely on building a model of your PSF that's slowly varying with time. And a face-on disk looks a lot like PSF wings, and it's really hard to separate the two. Ben has come up with a new technique called non-negative matrix factorization that better preserves the disk flux compared to the PSF wings. And with that, he's able to pull these nice sort of close to the inner working angle detections of some well-known disks that have been observed with SPHERE or GPI or CAC NERC2. And so now you get a long time baseline for some of these spiral structure type objects as well. This is, I believe, MWC 750 or 780. I'm blanking right now. But he has a NICMOS detection where you sort of pull out at least a position angle for some of the spiral structure. And you can compare that to 2015 and 2017 data to actually see if the spiral arms are moving with time. And you get some constraints on the time scale of that motion. And in this case, he doesn't see any motion, which kind of rules out some planet candidates that have been claimed for the system. And sort of predict that if there is a planet driving these arms, it's actually pretty far out. So that's kind of interesting. I encourage you to check that paper out. But we are also seeing debris disks showing some time variable features. This is AU-MIC. So a combination of STIS and ground-based data shows that these clumps in the AU-MIC disk are moving outwards with time. And I have a little movie that kind of demonstrates this. It's really quite striking. And we have no idea why this debris disk is doing this. Yeah, so it's very confusing. And now we're finding more clumps and even maybe some clumps on the other side of the disk. So it's kind of an interesting system as well. And all this really sort of boils down to the fact that because we now have high quality, high spatial resolution images of a larger and larger number of disks over longer and longer time spans, we're seeing that these disks are not static things, but change on sort of yearly to decadal timescales, which is very interesting. And in some cases may even help us to find planets at locations that are very challenging for typical direct imaging locations. So, at sort of the innermost planet forming regions. And it's just going to get better, right? Because we have James JWST launching soon, hopefully, where we can look at disks in space again with sort of in the near infrared. We can combine this with ground-based observations that have the ability to maybe look at things more frequently than would be possible with Hubble. And then if we look to the far future, I'm part of the WFIRST CGI, one of the science investigation teams for WFIRST. And the CGI will have the ability to hopefully have similar angular, inner and outer working angles similar to existing ground-based coronagraphs. So we will have the ability to sort of push these time baselines even further, especially in the optical. So you can look at some STIS observed disks now and in the past 20 years, and you can compare them to WFIRST in the 2020s or the 2030s, whenever it hopefully launches, and you sort of get an even longer baseline as well. So it's all pretty interesting, and hopefully these time variable features tell us something unique about these planet forming systems. So thank you, and I'll take some questions. Yes.
So this putative planet around TW Hydra. So 1AU, I'm assuming it's like 1 year period or something like that. If it's 1AU,
Yeah,
roughly speaking.
Yeah.
So you know, RDs are interesting. I feel like you get unlucky with Sinai that way.
Sure.
So have you? But it seems like it's within the realm of Gaia potentially, depending on how astrometrically noisy this system is.
I don't
integrated
have a sense of that.
Gaia flux.
Yeah, no, Gaia is definitely another way, and especially is perhaps more useful than RVs for these face-on systems in particular. I haven't run the numbers for what one Jupiter mass at 1 AU is.
What's the distance of TW Hydra?
The distance? Well, it keeps getting further with every Gaia release, but it's about 60 parsecs at the moment. So, yeah, it was 54 with Hipparcos, then DR1 said 59, and DR2 says 60.
So 1 AU is 20 high teens milliarc seconds.
Yeah.
The astrometric orbit would be 1,000 times smaller than that, roughly.
Yeah. So
maybe.
Rough. Yeah, maybe.
No.
On the low end of maybe,
yeah, that's
I
actually
think.
a little hard.
Yeah, and this, well, so the other problem, if people remember TW Hydra, there was a claimed like 3-day planet for a while, but that turned out to be stellar spots because 3 days is suspiciously similar to the rotation period of TW Hydra. But that should be less of an issue in the near infrared, which is why I specifically mentioned the near IR. So yeah, but yeah, either way, it might be tough. But I think even at the low inclination, Jupiter mass at 1 AU is still a pretty large signal. So if you can get sort of in the meter per second range, you can at least rule out that 19 Jupiter mass.
Yeah, I was going to say you might, well, and even astrometry too.
Yeah. Yeah. Maybe you could do a combination. Yeah. Great. Any other questions?
Maybe I'll ask one.
Sure.
I'm just curious, so in general, for observing those debris disks, what do you feel for using STIS versus GPI sphere? Like when each one?
Yeah, so I alluded a little bit. So if you want a larger field of view, STIS is definitely the way to go. If you're willing to spend a lot of time and you want something really faint, like Fomalhaut, it's gonna be really hard to do Fomalhaut with any existing ground-based observatory. So so I think the niche for STIS is either going back to something you've observed previously, so you get the long time baseline with the same instrument. If you care about sort of shorter wavelengths, then you go for STIS. And if you want really deep sensitivity or field of view, STIS is preferred. And then another good thing is that STIS doesn't necessarily care what the brightness of your primary star is. So there's going to be a regime where things can't be done in sphere or GPI because the primary star is too faint. You could still do it with STIS. Although eventually there's diminishing returns even with STIS because you won't get necessarily the same contrast depth. But